Thank you, sir. Almost there, folks. And it's official. Welcome back, everyone. We can get started. It's kind of a weird week. We're only going to be here for just Wednesday, but after this week, we should be all back to kind of a normal work week. Should say work week necessarily, but a normal week for the rest of the semester. I'm not anticipating any further interruptions. As far as that's not it, announcements go, I did make a mistake. I usually post a quiz on Wednesday, but it was a little bit weird because of President's Day. I think I just fell off my normal process. So no quiz this week. I just simply forgot to write one. We'll get back on track for that for the next week. We also have quiz 4 and quiz 5 due today. But if you're behind on any one of those, that's going to be okay. I will accept late quizzes in this course. And think of, again, the due dates mainly as a benchmark for being totally caught up is the best way to think about them. So if one of the quizzes you just didn't get to, feel free to go back to that material, redo that work, and I'll be happy to accept it. Well, we're in section 3.4. We're going to take a look at the product rule, the quotient rule. But before we get into that, we also have midterm weeks coming up next. And that can be oddly stressful, but for our class, there is no special midterm exam, midterm project, or assignment, or anything along those lines. Essentially, what's going to happen on midterm week is on Friday, I will go up to here, include anything from WebAssign, those kinds of things, update your grade. It's usually updated about twice a week. And that's going to turn into your midterm grade, just your current grade on the end of Friday of that week there. Any questions about that so far? Okay, so there's no special midterm exam or anything like that. At IUC, midterm week is more about just reporting where you're at halfway. That way, if things aren't going as well as you anticipated, you can do things like schedule meeting times with your professor, office hours, and things kind of along those lines. But just because there's no exam that week doesn't mean there's no exam on the table. We scroll even further than midterms week. Well, we still have a buffer week right here before we're getting on to the second exam. That will be Monday, March 11th. So just like we mentioned, everything on Moodle just sort of repeats as a cycle. When we get close to the weekend of this week here, March 4th through March 10th, you'll see more information published, the review kind of documents. And the more important document that you'll see is the analog to this one right here, the exam 2 formula sheet. I'm going to try to get that one printed early so you have a good expectation of what to be memorized and what you can rely on the real exam. Well, I think that's my full spiel for announcements, folks. Any questions or things we missed that we should discuss? Okay, well, let's take a look then, finally, at product and quotient rules. Now, it's kind of alarming when you open this up and then there's a yellow caution and a bunch of things here saying product rule should not be used and so on. But the reason for all this that you see in the notes is there's a particular thing that happens in a calculus class where in your section 3.3, we're using power rule over and over again on different problems. But in section 3.4, we discover this really powerful rule. We study it really hard, we get fluent with it, but you don't want to get too fluent with it. That's kind of weird. What I mean is you have to know when to use this very, very powerful formula, and we have to know when there's a simpler method that we should use instead. The reason that's such importance is because this caution right here. If you use a product rule in a problem that really the product rule doesn't go along with, like this one, the process is longer, and in some situations it can be just unapproachable. Even on an exam setting, there's just too much stuff to write out. So this is a context where we wouldn't use a product rule. Let's start right here. This will be our warm-up question for the day before we're getting into that one. So if you see this as a function you want to differentiate, the unfortunate fact is you can't differentiate this one and then multiply by the derivative of this one. The derivative would just come out wrong. In fact, if you did, that would be a derivative of 1 here, a derivative of 2 here, but this derivative is absolutely not 1 times 2, it's something else. If you see 2 functions being multiplied, but you suspect you can expand them out, this should always be the first step. Just rewrite f of x. Well, you distribute x plus 3 through using the FOIL method, so it'll be x by 2x, x times negative 1. Next, distribute 3 through, we'll get plus 6x, minus 3, And so f of x altogether is 2x squared plus 5x minus 3. Now, you know that we can work with. Differentiating this is, in fact, just really, really fast. We'll get f prime of x. Now we're just using the power rule, the constant multiple rule, the sum, and the difference rule. I mean, that's a lot of derivatives altogether, but the process is a lot simpler than it seems. You just differentiate 2x squared. This will turn into a 4x. The process was 2 comes down and multiplies. The power here is 1 less. Derivative of 5x just turns into a positive 5. And the constant negative 3 vanishes. And there we have it. The ordinary derivative is 4x plus 5. Now, if you did hit this with the product rule, here's another reason why this is kind of a terrible approach. The product rule here, it will give you that answer, but you now have to simplify it down to get to that expression. And sometimes the simplification can be a lot. So if you notice your answers just aren't working in WebAssign, it could be that kind of issue. You didn't simplify it, and there could be a lot of simplification work to get through. So this is a case where product rule is a bad idea, because if you expand the function, older methods work. But over here, there's no such luck. There's just no way to expand x cubed times e to the x without using weird methods. That's going to help us differentiate. We have to do this one directly with the actual honest-to-goodness product rule. Well, how's it go? The structure is, if you have a function f times a function g, and you're differentiating it, so a prime, or in Leibniz notation, d by dx, it's an interesting pattern. You write f times g twice, separate it by the sum. You'll differentiate the first function here, copy the second function, then copy the first function, differentiate the second. This turns out to be exactly the right thing to differentiate that kind of function. But let's give it a try. So in mathematics, another weird thing that happens is you'll see formulas stated this way because, well, we have to describe it in this way. We have to say what we mean and mean exactly what we say. But the way we use the formula is not necessarily directly copying that down. We want to think of this as a formula as a kind of structure. We're going to write g prime of x equals, in place of f prime of x, just put a placeholder, just a parentheses that goes like this, and a prime symbol on it to remind yourself to differentiate that term. For g of x, we do another parenthesis, then copy and plus, and 2 more parentheses, one for f of x, and one for g prime of x. But for that one, definitely put in the prime, again, as a reminder to differentiate on that term, or that factor right there. Then after we do that, the pattern is you drop x cubed here and here. In the first slot, it's being differentiated. The second slot is being copied. That's what's being communicated here with the prime and the missing prime. Then just go to the second function, it's e to the x, and drop it into the remaining placeholders. E to the x goes here and here. So this structure right here is really helpful if you're memorizing the product rule or coming up next to the quotient rule for the first time. But once you get pretty fluent with this, this is a pretty common shorthand. I'm not going to take this shortcut on the notes because, I mean, we're learning this stuff. That would be rude. But if you feel like you're getting to that point, even on these notes, it is an appropriate shortcut to take. In fact, this is the goal, to be fluent enough with the product rule that you don't necessarily have to write this down every time. It's going to come down like this. You'll know you're differentiating x cubed, so you'll go 3x squared. That's what we said in the structure. Then the next thing is copy down e to the x. Plus just copies in. Next, we're copying in x cubed. But then multiply by the derivative of e to the x. That one's weird because when we write down e to the x, we did it, folks. That one's been differentiated. Just no change on that function. So our goal is to see it this way. We differentiate the first, copied the second. Start all over again. We copied the first one in and differentiate the second one. Finally, that's how the quotient rule goes on this thing. And really, it's not too bad. This is a function where you would really want to use the product rule. And in this one, it just makes everything a little bit worse if you did use the product rule on this one. Lots of extra steps, and then you have to simplify down to that. But that's pretty much how the product rule goes, folks. Any questions about it so far? Okay, well, I didn't use color coding down right here because I already had orange and green here. But sometimes when you think about these, if you did decide to color code them, this is not a bad way to go. Think of F as a function in green or blue and G as a function in green. Sorry, colors are hard today. Then this is the pattern of attack. We differentiate in that way. If you're using Leibniz notation, same kind of thing, except that when you put down a differentiation operator, d by dx, like this, you always want the function right here to go inside, and something that's not being differentiated would go right here. So we have this going in, and this going in, and that's the term on the right-hand side. In Leibniz notation, it's written out this way, just so that they have the differentiation operator there. Then likewise, we put in g of x, and f prime of x is okay right here, but in Leibniz notation, you want your f prime to be on the very far right, so there's no miscommunication of g being differentiated, because it's just f. So in Leibniz notation, this carries down like that, which is kind of weird. But oftentimes when we do this kind of process, we're usually focusing on the Newton's prime notation, more so than Leibniz. This is more here just for completeness. Well, any other questions or comments so far, folks? Okay, so that's the product rule. And it doesn't seem important yet, but that's highlight worthy in a certain sense. You want to memorize that product puts a plus right here. And if we change it to a quotient rule, there'll be a negative sign in that position and a denominator as well. Okay, well, let's practice out a couple product rules just to see how they go. My first one is motivated by a problem that you'll see in WebAssign, and it's kind of nasty. It says differentiate this. We'll probably need a little bit more space, so let's just grab some to start out. So if you're differentiating that function, it is two functions being multiplied. It looks like a product rule. But this is one of those kinds of problems where if you did hit it with a product rule, it'd be kind of a terrible time. This one is the one you really want to use the product rule on. And this one, it's now just effectively a review problem. Let's put a quick note here. Product rule is not necessary. And makes this one harder. So why is it not necessary? It's because you could just simply FOIL this out, expand them and differentiate like we did on the very first problem of the day. Makes it harder. This one would be really hard to simplify if we just hit it with the product rule as it stands. So instead, here's how we're going to think about this one. We're just going to use a bunch of exponential notations or exponential laws. So 3 divided by x, that's the same as 3 times x powered negative 1. 5 divided by x cubed is the same as 5 times x powered negative 3. That's a much better format for us to work on. This one's a 4th root of x, but that just means it's x to the power of 1/4 on this one, minus 1. Now in that format, we can just simply start expanding things out. But notice you might want to do some surgery on some of these exponents. Maybe we'll do it on the next step. Let's expand this carefully. First, here to here, it's 3 times x to the power of negative 1. But that negative 1 is more easily understood as a negative 4 divided by 4 because it's multiplying x to the power of 1/4. What we want to do is add up those exponents on the very next step. And this is a good one to actually write that down because a lot is happening with the exponents. The x product is nothing major. Here to here is just going to be negative 3x powered negative 1. Then we'll continue to expand. But from here to here, we want to correct this exponent as well. It needs a denominator 4, so we're going to call that one negative 12/4. So this will be plus 5 x to the power negative 12/4. Let me circle these temporarily. So we changed here to here, and the negative 1 went to negative 4/4, only to make the denominators compatible, because this one multiplies x 1/4, and that will go there. Last, multiplying here to here is going to give us minus 5x power negative 3. And we're just about ready to start differentiating, but all we're going to do is combine our like bases here and here. Any questions so far, folks, to this stage? Okay, how do folks feel about the exponents, though? Any questions about them at the moment? Okay, if we're happy with those, then the good news is we're just about through the problem. This is kind of the worst step. Expanding this out is definitely nasty to look at first, but here's how it's going to go. This will be 3. Exponents multiply, or excuse me, add together when the base is x multiply. So negative 4/4 plus 1/4 will give us negative 3/4. Then on this one, no changes required, so just go minus 3, x power negative 1. We do need to make a change here. Let's combine like bases. Write the base x once, and it's negative 12/4 plus 1/4, so we get negative 11/4. Last, copy down this term, minus 5, x power negative 3. So definitely a lot of exponent work that we had to get through to get to this stage. But this is where we want to be, because now we can just simply say y prime, or dy dx if you prefer, will be the result of term by term by term by term differentiation. We'll just go left or right and work it out. Well, let's give this a try. This is a pretty good review problem on its own. When we get our first term, anyone see what it would look like to start us out? Yeah, go ahead.
3 over the fourth root of x to the third power.
So 3 over 4th root of x to 3rd power. Let me think about that. I kind of lost on that step, but let me show you what I would probably write to start this one off. You might be at a further step than I am on this one. I'd probably start by keeping that 3 right where it is. I would multiply it by that thing times negative 3/4. And then the new power of x would be found by subtracting 4/4. So we subtract 1 from it. It'd be negative 7/4 altogether. And so that's how this first term would come down to start it off. Definitely kind of a weird process, though. Essentially what happens is, by the power rule, this multiplies right here. So we have the multiplication there. And then after that step, we take this negative 3/4, subtract 4/4 to get that negative 7/4 out. So our big superstar for that first term was the rule d by dx of x to the power becomes that same power times x to power n minus 1. So we reduced it by 1 from here to here. But does that make sense to folks so far? Awesome. I think this one is really kind of challenging because although we're using the power rule in the normal way, all of these exponents are kind of non-standard when you look at them. And so it's extra tricky to get through this kind of work. But once we see what the tricks are, it becomes just kind of rinse and repeat when you see this one as a WebAssign problem. Same issue on this one. We use a power rule, negative 1 multiplies here, forces it to a positive 3. But on x, any volunteers for what the new power would be right here? Exactly, we'll just subtract 1 from it. If it's negative 1, we're dropping down to negative 2. So that's pretty much our mantra, always 1 less. And keeps on going. This negative 11/4 will multiply 5. Let's write this in this additional step, 5 by negative 11/4. Then we write x in, but for the power, we're subtracting 1, which means we're subtracting 4/4, and that becomes negative 15/4. So that's 3 down, 1 more to go. On this one right here, how about for someone over Zoom? Anyone have what this should come out as upon differentiating?
15x to the negative 4.
Awesome, thanks for providing that. So plus 15x to -4, exactly as you said. The -3 came down, converted it to a positive 15, and then just one less, -4 there. At this stage, we are almost there, but we still have to simplify our answers. That's just going to be multiplying these through. So we can now say that y prime, on this first term, we get -9/4, x to the power of -7/4. No change here, so plus 3x powered -2. This one will multiply through to get -55 fourths times x powered -15 fourths. And then another copy, plus 15 x powered -4. And we did it, folks. This one's pretty challenging, but the reminder on this one is, if you did use the product rule, it's not fun. It's a slog. It looks worse than this, and you have to simplify it. It's terrible in an exam setting to try and work them out like that. And that's why we're emphasizing when to use a product rule and when not to use it. This is definitely we want to use it in this case. But that one looks exactly what you would want for a product rule type problem. We'll hit it with the product rule on this one next. Any questions so far before we start this one off? Okay, maybe let's look at these two a little bit more closely. The reason we didn't use a product rule on this is because we could just simply FOIL it out, expand, and differentiate termwise. But this one, it's a function of t times e to the power of t. There is no way to expand that out. This one requires product rule no matter what we do. So if we know that we're just going to deal with a product rule, here's a decent way to start off. I'm going to think of everything, including the coefficient 9, said everything, 9t cubed, including the coefficient 9, to be the first function, e to the t to be the second function. Then product rule goes like this. Let's write first that product rule. It's not just a good idea, let's say is required for this one. So we'll get f prime of t equals, and this is the structure. When you're learning product rule, this is a great way to begin, because all we're doing is putting down blanks and dropping in the right things into the right positions. And the way it goes is put down two blanks, a plus and another two blanks. This is actually easy to forget, so don't forget that two things have to be differentiated. The emphasis is in yellow. But thereafter, you're just plugging things in a methodical way. 9t cubed could go here. But if you did that, 9t cubed will be the first factor here as well. Likewise, e to the t is the second factor. And so it should be the second factor here where it's differentiated. Over here, it's just copied. Then at this stage, we're pretty much ready to go. We differentiate this function. It's weird that the variable is t, but just think of it as an x. Same process. That 3 will multiply that 9, giving us a 27. And I almost wrote x. The power on t, not x, is 1 less. So this turns into power 2. Next thing, just copy e to the t. Copy in the plus. This is another copy, 9t cubed. And differentiating this one, the best derivative of all time, you just get e to the t. Finally, that's pretty much our answer. And looking at this, there's not too much more you could do to it. You could factor out the greatest common factor. That would be something like 9t squared e to the t. But unless you're doing something further, like maybe an optimization problem in chapter 4, there's really no further work to do on this. No terms combined, there's no cancellation. Factoring is just an optional way to represent your work. So I'd probably just stop at this step for this kind of problem. We did it, folks. That's our product rule. Any questions on getting through this one? Okay. Well, on our next one, product rule would be required for this. And the reason is, when you multiply the 2x times the 4e to the x, that's not too different from this problem. So this one's even a little bit weirder. There's extra rules that we have to get through on this one. And it's also a reminder of something weird that happens in calculus. Every time we get a new rule for differentiating, they interact together. So this one is going to combine constant multiple rule, sum rule, difference rule, and product rule in one whole problem. But our goal is just to become so familiar with doing these kind of differentiation things that it's an automatic process. This one, you have a couple options. You can either start with the product rule immediately. If you FOILed first, you might simplify it a little bit and the product rule will be easier, but it's really completely up to your option. I wouldn't necessarily say that there is a best approach on this one. So what I would probably do is, I'd probably mix the approaches. Let's expand it out by FOILing 2x minus 9 with the 9 e to the x plus 1. G of t will first be this 2x times 4 e to the x. So that's 8x e to the x, then plus 2 to the x. Next, distribute the negative 9, and we will get negative 36 e to the x minus 9. So that's our whole function. And the nice thing about this function is the last three terms are extremely fast to differentiate. So that helps us out because we expanded. But the first term, that one is a product rule. There's no getting out of it. So we saved a little bit of time by expanding, but we will still use product rule right here. So the product rule is required, but only in that location. So that's kind of weird. We're mixing multiple rules all at once. That means we can start to color code this if we're just using the product rule there. And let me try to write that in better. I wrote in e to the 4. That should have been an e to the x. I think I see what I did there. The 2 and the 4 came to an 8, but that I was still thinking 4 probably. Let's put in the actual x there. And we'll use a product rule in that statement. So we're about ready to go. We can say, let's hide that quotient rule for a bit. We're not quite ready to look at that thing. We'll say g prime of t, since the variable is t. Well, I think I have a typo here. Sorry about that, folks. I indicated a t, but this one should have really been an x. I should double check all my notes. I think this is the second time that's came up. Let me put that in red for indication of a quick edit on that one. Over here and over here, those should all say x. Okay, again, sorry for that weird distraction. I probably should double check my notes before I launch them for those weird issues. They've been coming up. But now g prime of x, we're back on track. It will look like this to start. First, let's focus on the product rule. Okay, we've got our parentheses down. Then the process says e to the x goes into the first positions, the first factors, you could say. E to the x will go into the second factors. So here and here. But then because we're mixing rules, we start to pick up the differentiation process on all the last terms. Derivative of 2x is just a 2. This one is a product, or excuse me, a constant times a function. So this one's not a true product rule. You just copy down the negative 36. Take the derivative of e to the x. There it is, it's itself. And then that takes care of this one altogether. But that's a good reminder. If it's a constant times a function, let's also indicate here that this is, although you could use a product rule, you really shouldn't. So I'll just say not the product rule. That's definitely a good note to make because, again, if we use a product rule on everything, sure, it works, but then we're taking a ton of additional time. We're just not going to move through the problems fast enough to complete an exam, for example. So this one is just simply negative 36 e to the x. That was a constant, so nothing happens. It goes to a 0. And we're well on our way, but we're not done because we have to differentiate here and here to finish it off. But any questions, folks, to that stage? Okay, let's finish off that derivative then. So next line, the derivative of g at x becomes this one, nice derivative. Derivative of 8x is just 8 because the power of x is 1. Copy e to the x. Then copy positive 8x. This one we've encountered quite a lot. Derivative of e to the x is itself, so we just throw that in there. And everything else we've already differentiated, so we just copy these down. So plus 2 minus 36 e to the x. So finally, that's our result. The derivative is all of this stuff. But when we look at this, this is probably a problem where WebAssign might complain at us and not accept the answer. Because we have 8 e to the x, negative 36 e to the x. Those are like terms. And so our last step will say g prime of x equals negative 26 e to the x, combine the like term on the far left with the far right, then plus 8x e to the x plus 2. Finally, at that stage, we've got it, folks. That's our end result. Any questions at all on getting to that one? Awesome, glad to hear that. I'd say this one's kind of challenging because of all the different rules we had to use. And we went the approach of foiling first. If you use the product rule first, you'll get to the same answer. It'll just look a little bit different. Yeah, go ahead. Oh, absolutely. Thanks for spotting that. 8 and negative 36 combined to negative 28 altogether. Really odd arithmetic. Thanks again for spotting that one. So negative 28 e to the x. It's always weird to be doing calculus, but getting foggy on the arithmetic on these problems, but it can happen. Other questions with this one? Okay, well, that's pretty much all I have to say with the product rule for this kind of function, or for these kinds of functions. You notice e to the x came up a lot. That's because we don't have a lot of material actually to really combine product rule with until we get the logarithmic functions. We'll see that in the later sections. But the same scenario is not true with the good old quotient rule. So here it is finally. Like before, I've stated it twice. I've stated it using Newton's prime notation, again in Leibniz notation, just for the sake of completeness, although we don't often use it in the Leibniz notation below. But what I would want to copy right here is the product rule again. It turns out it's kind of easy to memorize both if you're thinking of the quotient rule just being a new rebuild from the old product rule. So if we restate it, it goes like this. A function f of x times another function g of x prime. I stated it by writing in f prime of x, g of x minus f of x. Oh, that's a plus right there. Definitely put in a plus right here. Times g prime of x. So for product, we throw a plus right inside there. But if we're doing the quotient rule, a minus goes in. Notice, however, it is still f prime times g minus f times g prime. So it carries over this same exact structure. We're just doing a sign flip in the middle. Then the thing that's definitely new is that denominator right there, g of x squared, completes the quotient rule. So think of it as terms of color coding. We're pretty much going like this. Differentiate and copy in those locations. And this time g of x goes into 3 positions. It's copied here, differentiated here, and then squared down there in the denominator. So that's our full statement. And same caution as the product rule carries over to the quotient rule, but this one is even more dire. If you use quotient rule on things where it really shouldn't be used on, you can make a huge problem out of something that should have been actually pretty fast to maneuver through. That's something like this one, well, a version of it. This is one where we shouldn't use a quotient rule, and yet this is one where we must use the quotient rule. There's no other great alternative to the one on the right. And that's weird because notice how similar these functions look. So part of our goal when we pick up the quotient rule is also knowing the best time to use it. These 2 examples will help us out, so let's give it a try. The reason you can't, or I shouldn't say can't, the reason you shouldn't use a quotient rule in this one is because the function simplifies. And it's really more about the denominator contained one single term. That allows us to take f of x equals x divided by x plus 1 divided by x altogether. So then this will simplify to a 1. And this one is not the quotient rule. It's always a good reminder because it sometimes is tempting to use a quotient rule on 1 over x. But if you write it like this, you just saved like 3 or 4 minutes potentially on an exam setting, because now it's suddenly not a quotient rule you'd be using, but rather the power rule instead. So that's how the function simplifies down, 1 plus x powered negative 3. And that means the derivative of f of x is immediate. The constant vanishes. Sorry, question first? Yeah, good question on that one. That should have been a negative 1 right here. I'm not too sure what I'm doing with my constants, but that should convert to negative 1. Thanks for spotting that one. I think I'm just rusty. The vacation was too long for us, maybe. So the derivative on this one vanishes. But with the correction, negative 1 carries down. And the new power will be negative 2 altogether on that one. Again, thanks for the 2 corrections so far with these. That look all right to folks so far? Okay, so we used just our ordinary methods, but we had to simplify the function first. Reason that doesn't work over here in green, where we will use the quotient rule, is because there's 2 terms in that denominator. There's no great way to clean that up. And if you use long division, you're getting infinitely many terms here with negative powers. That's not a good approach either. In this case, we just have to use this structure and hit it with quotient rule. So here's our first example of that. G prime of x. Well, if it was a product rule, I'd probably go like this. Because it's a quotient rule, throw a negative right here instead. And that's the only difference so far from the product rule, that negative. The second difference is down below. We put something squared. So that's the formula. It has to be written this way mathematically. But this is the structure. This is the way we actually use it in practice after we see the formulation of it above. Next thing, we're going to match up our strategy. X will copy into this location and into this location. Now, a good way to memorize the quotient rule is that the denominator gets copied into 3 different positions. It'll go here, here, and here, where it's squared in the denominator. So that's the full setup. All we have to do is crank out 2 derivatives and any simplifications that are left over. First, that'll turn into a 1 times x plus 1. Here we'll get negative x. Derivative of x plus 1 will be a 1 plus 0, so that's just a 1 as well. Put it times 1 just to say we did it. There's the result of that derivative. And nothing special happens in the denominator. Just like when we were doing the derivatives from scratch, using the definition of the derivative, there's usually no value in expanding this out. It's actually better if it's in its factored form, because it allows us for a chance to cancel something in the numerator if there was a possibility of a cancellation. But here, doesn't look like it. This is turning into, in the numerator, x plus 1 minus x, after the multiplications by 1, divided by x plus 1 squared. Last thing we have to do is simplify, but that's just x minus x, giving us a 1 over x plus 1 squared. Then at that stage, the whole process is over. That's how the quotient rule goes. Any questions with that so far, folks? Okay, and again, it seems kind of silly, but this is actually a pretty good remark as well. You definitely wouldn't want to use quotient rule on this thing, because if you did that every time, it's just going to be a really long slog to get through all the problems. This is a really big idea as well. Try to convert things so that you're never using the quotient rule when you don't have to, and that's a huge time saving on that step. Because you'll observe, if you use quotient rule on functions more involved than this, it turns into a lot of stuff. It's worse than the product rule, and the simplification phase can be pretty involved as well. Well, let's take a look at some of the problems down below. Any last questions at all, folks, with either of those 2 versions? Okay, well, here's our first problem to start us off. It just says differentiate. That's kind of nice instructions, not too much going on there. But when you look at this one, there's no way I can simplify this to avoid a quotient rule. If it looked like this though, that's the nice problem. Just divide x into both terms and you can get through the problem really, really rapidly. But that one is always a little bit extra. We can think of it as a top function for blue, a bottom function for green. For differentiating, that means our result will be dy dx. And here's that structure one more time. Let me make this a little bit longer to fit it all in. We do two parentheses. Because there's a quotient, we'll put a minus in the middle. Another set of parentheses, but observe the prime should be on the first factor of the first term and the second factor of the second term. Then down below, square something. Any volunteers for what should go into that first position where it's being differentiated?
2x plus 1.
Good call. Always the top function should go there if you have a prime on that location. So 2x plus 1 here. And then it copies here, not differentiated. Next, x plus 3 copies into all of the remaining positions. So if you know where the numerator goes, that's great because it pretty much pigeonholes your denominator into everything else. So x plus 3, x plus 3, x plus 3 quantity squared. All that's left to do now is just differentiate this, simplify as much as possible. Actually, let me go down vertically, just in case there's a few extra steps. And let's work through it. I'll put in blue just to show which ones we differentiated. Derivative of this one will turn into just a 2. That's a linear function with slope 2, so the whole derivative is now 2. Nothing happens here, so I'll just copy it in black, x plus 3. Minus, no change on 2x plus 1. But we are differentiating this. It's just a kind of a nice derivative. The 3 goes to 0 because it's a constant, and derivative of x will go to a 1. So we just throw it in like that to remind ourselves we did differentiate it. And down below is x plus 3 quantity squared. Again, nothing happened down there. It's best in its factored form. What we must do on the next steps is simplify all this stuff. There's nothing too major. We're just going to distribute 2 inside. That'll be a 2x plus 6. Here, the times 1 vanishes, and we're just really distributing a negative inside. So minus 2x minus 1, all divided by x plus 3 power 2. Then it's still not done. Sometimes when you begin simplifying, you open a can of worms. So on our next step, 2x cancels out with negative 2x. We get 6 minus 1, and so our whole answer is 5 over x plus 3 to the power of 2. And we did it, folks. That's pretty much how the quotient rule goes each and every time. I mentioned this step right here. It's optional, but it's a good idea if you're memorizing quotient rule, working it the first time. The goal is, once we move past chapter 3 and chapter 4, we'll probably start differentiating in this way, skipping right to that step. What we'll do is just observe. We need the derivative of the top function. That's 2, so copy it in. Copy the bottom function. Then top function goes in, copied. We multiply by the derivative of the bottom function, so we'll just write times 1, and then square the bottom function. So our goal is to try to get to that stage. But in the meantime, this is massively helpful for us to get to that stage. Well, let's try out another one just for the sake of practice. But any questions first at the moment? Okay, well, here's our next setup. This one is involving exponential functions again for us to deal with. And our hope of hopes is that we had the reciprocal of this function. If it was written this way, f of x equals e to the x plus x divided by e to the x. Well, you know what? That one would still be the quotient rule because you would get e to the x divided by e to the x, which is a 1. That simplifies the problem, plus x divided by e to the x. That would still be the quotient rule. So yeah, this function is not great, even if you look at the reciprocal on it. because right here is still quotient rule, even upon simplifying. So this one is absolutely quotient rule because of the two terms in its denominator. Let's take on this one and see how it goes. First, color coding is not necessary, so you don't have to bring color-coded pens and things like that to the exams. Think of the color coding more as something you could use on your notes if it's helpful, but it's more for readability if you come back to these lecture notes. So we're going to the derivative, we'll indicate f prime of x. It's a quotient rule, so we'll go like this to start out. Definitely don't forget the negative sign in the middle. That's an easy one for me to miss. Down in the denominator, we'll just square something. And like before, it's pretty easy to set up once we know what the structure looks like. We'll copy e to the x here and here. The remaining stuff goes, well, everywhere else. E to the x plus x, e to the x plus x, and e to the x plus x there. So we're just about through. Let me see if we have enough space. Let's move in a little bit more on this one. Next stage, we're just differentiating as we go. So write that this is equal to derivative of e to the x. I'll keep this in blue since this is the one that, in a sense, changed because we took a derivative, but it's the same function. This one we're copying, so I'll bring it down back to black. Nothing happened on this one. E to the x plus x minus, you can drop the parentheses on this one and just put in e to the x. But on this one, we absolutely do need parentheses because this e to the x has to distribute through the result. And this result contains two terms. We'll differentiate e to the x first. There it is. Then differentiate the function x. That turns into a 1. And so that finally finishes out our numerator. Really, I didn't do too much. Everything in black was directly copied down. And we also copy in e to the x plus x quantity squared as well. So the new changes are color-coded there. And now when we get to this step, this is where the adventure begins sometimes with these kinds of functions. We need to simplify it. And the need for simplifying this is more than it seems. In chapter 4, let's put this as a temporary mark. In chapter 4, we need to solve this equation. We'll set our derivatives equal to 0, and that's a terrible equation to solve in its current form. The more you simplify this, the easier chapter 4 becomes because we can actually solve that equation in a faster way. But also, WebAssign is picky with simplifying, so we should do it for WebAssign's sake. Here's how it's going to go. First, we take e to the x times e to the x. That turns into e to the 2x. That's kind of confusing already on its own. You can visualize it this way. E to the x times e to the x. The product rule formula is that you always add exponents. So x plus x, resulting in 2x, is how we're getting that term right there. Then multiply here to here. This is unlike bases, so it just turns into x times e to the x. And that finishes out the first distribution. Next, we'll do it again with the negative e to the x over here. So multiply here to here, and we get minus e to the 2x. Here to here will just be minus e to the x. Then finally, the whole thing is being divided by e to the x plus x squared. It's kind of tedious, in all honesty, to copy this denominator every single time, especially with the knowledge that nothing's going to change there. I encourage you to do that. Your head will get stronger, so that's one benefit from all that practice. But it's actually easy to forget there's a denominator and not report it on your final answer. So there's a lot of protection, especially on exam, on being methodical with that kind of stuff. Beyond that, e to the 2x and negative e to the 2x cancel. And that just leaves these two terms left over. It's completely up to your option if you want to factor them. Usually in chapter 3, I would just leave it like this. X e to the x minus e to the x divide by e to the x plus x squared. So This function differentiates in this way. The simplification is sometimes as hard as the derivative. That's kind of wild in a way, but this is where it settles on. If this was a real exam question, let's say it was out of 10 points, I'd probably give half the credit for just writing out this. You told me you know what the quotient rule looks like. I'd probably give the other 4 points out of 10 for this. You differentiated correctly. And everything else is still important, but this is more algebra at this stage. Out of a 10-point question, I'd probably consider that 1 point. Still important, we have to simplify them, but the real thrust of the question is the calculus right here. So that's how partial credit will typically go for exams. Well, this one is tough, I would say. Any further questions, folks, on getting through that one? Yeah.
Can you tell me how you got x and u to the x again?
This one right here?
Yeah.
Oh, gotcha. I think it came from when we multiplied here to here. And when that multiplication happens, it looks like this to start, e to the x times x, but then I just rearranged it. I put x first and then e to the x afterwards. Does that make sense on that one?
Yeah.
Awesome, thanks for that question. Other questions at the moment? Okay. Actually, let's leave that there. That is a good explanation on that one. Let's see what we have next. Part C is getting even worse on us. That's kind of awful in a certain sense. But the reason I brought down part C is some of the problems in WebAssign do get a little bit complicated. This one's a little bit worse than the WebAssign problems, but that means it's good practice for us to see how to delve into a problem like this one, where there's a lot going on. Now, if you look at this, let's really zoom in on this thing. It's a quotient rule to start. When you differentiate the numerator, that's a sum rule, so that's 2 rules. When you differentiate the denominator, that's a difference rule, so 3 rules. But right there, that's a product rule. There's 4 different differentiation rules all rolled into one on this thing. That's kind of nasty. It means we should work very, very carefully and methodical whenever you see something like this one. Organization is almost more important than anything else, so let's organize by color coding. Start by writing g prime of x equals, first here's the structure. Don't forget the prime like I very nearly did. Minus goes in the middle. Oh, and I'm copying in too much. Let me put it in this way. Let's do it how we normally would. Once we have that down, we're dropping these things into their appropriate positions. X plus e to the x goes here and here. Then this function goes everywhere else. 1 minus x, e to the x, 1 minus x, e to the x, 1 minus x, e to the x, quantity squared. Now that we have this, there is one problem with this whole thing, and it's right there. Well, there's one issue rather, not necessarily a problem with what we wrote. The issue is when you differentiate that, you get 2 more terms. You have to keep parentheses around them because this is going to FOIL with whatever you get right here. But sometimes when you see all this going on, here's an alternate strategy you can take. Let's just pause on the quotient rule right here, handle this like a completely separate problem, find a formula for it, we'll plug it back in. So we're segueing into this now. Let y equal 1 minus x, and let me put it in green just to match that color coding. Y equals 1 minus x, e to the x. The process here is divide and conquer. If there's too much going on, break it up into chunks. Don't look at the whole forest, just focus on one tree at a time is what we're trying to do. So we're going to start right here. Y prime equals, let's put that in yellow because whatever we get, we're going to plug back inside here. The derivative of this, well, that's a constant, so it vanishes, it's gone. We will need to take the derivative of that portion and that portion. Right here is the product rule. Let's just circle this just so there's a paper trail in the notes. So if it's product rule right there, again, no change on the first term, and let's see if I can zoom out just a touch. There we go, that should go. Don't want to hide the participation window, that would be rude, I'd say. So to start this one off, I'm going to use this structure. Because it's a product rule, recall plus in the middle. Now I'm going to think of the negative x as my entire first factor. So they'll copy in here and here. This avoids issues of distributing the negative sign into your final answer, so this helps us a lot with tracking that negative sign. Next, e to the x goes into the remaining positions. And now we differentiate as normal. First derivative of negative x is just -1. We'll write it as a negative sign because it also multiplies e to the x. So just negative e to the x. On this one, we can drop parentheses and write just negative x, which also multiplies e to the x. And that's the thing in yellow that we're going to connect right inside here, returning back to quotient rule. Well, any questions so far, folks? Okay, now that we're at this stage, it's not as bad. That derivative is just the sum rule. We didn't need to worry about it as much. We're not going to expand that. There's really no value in it. And we're just going to plug in the derivative right here. So we're on our way to simplifying this down. So g prime of x will track the equality down and try to simplify this as much as possible. We're starting with this function. We still have to differentiate it. For the x, we'll get a 1. For e to the x, it's just going to be itself. And then that one's done. It's fully differentiated. Copy on here, 1 minus x, e to the x. More copying up to that position, so minus x plus e to the x. And here's where we are making a substitution. This derivative came out in this way, so minus e to the x. Minus x times e to the x. Let me put that in yellow just to track that substitution as well. Now we have the numerator settled. The full denominator is 1 minus x e to the x squared. Now our adventure at this stage, and it is an adventure, is to simplify this down to a nice answer. And that's actually, in my opinion, almost a little bit harder than the calculus sometimes. So we'll track those next steps carefully. But first, any stage or any questions to get to that stage? Okay, let's work through the simplification next. We're just foiling things out, but we want to do it carefully on here because of the interesting non-standard looking functions. First, we'll multiply, get 1 by 1 for a 1. 1 times negative x e to the x is minus x e to the x. Now next, switch over to distributing e to the x through. Here it's just plus e to the x. And here to here, it'll go minus x, but then it's e to the x times e to the x. Let's write that in the margin just for a reminder. That always just looks weird with exponent laws. It turns into e to the 2x altogether. So that finishes off the first distribution. And on the second distribution, it's kind of unfortunate that there's a negative sign right there. Because once we FOIL this through, we still have to handle that negative sign. There is an interesting way to go around this, though. I'm not going to do this on the notes because it's pretty confusing, but this is a pretty good shorthand for your work, homework, quizzes, and exams. You could convert that to positive. That means you distributed the negative sign into one of the groups or the other, but not both. Distributing into this one makes sense because then you would get plus and plus. And now you're distributing without the need for a second distribution with the negative sign. It's a pretty effective way to get through this one. But for the notes, that would be really confusing to read it through. I'll do it in the long form way. And if you're taking the shortcut, we can compare our results. So I have to start with a negative and an overall parenthesis. And what's going inside here is just the result of another set of foiling. This will be minus x times e to the x. Here to here, this time the x's multiply, so it's minus x squared. e to the x. And let me open up that parenthesis. I don't think we have enough space to fit it all in. Next, here to here will be minus e to the x times e to the x. So that's a e to the 2x once again. And here to here will be minus x times e to the 2x. Okay, so our numerator got nasty. It always gets worse before it cleans up, it seems like. Our full denominator is 1 minus x e to the x, quantity squared. And now I'm going to do a whole bunch of copying. The only changes will be right where we distribute the negative sign through. It's just going to convert everything here to positive quantities or positive leading coefficients. So we'll get 1 minus x e to the x plus e to the x minus x e to the 2x. And it's good to go slow here. With this many terms, it's easy to just misrecord one of them. Let me know if I miscopy something. Now distribute the negative sign through to get plus x e to the x plus x squared e to the x plus e to the 2x plus x e to the 2x. It's a lot of stuff all of a sudden. And all of it's divided by 1 minus x e to the x squared. Okay, after doing all of that, here's our reward. We have loads of cancellations that we can do. First, we have negative x e to the x. Let's see here. There it is. Oh, no. There it is. That's its like term. So these two would cancel off. Next up, we've got, let's see, e to the x. I don't see any things to combine with that one. But we do have negative x e to the 2x. It's out here, canceling with this one. Now, after that, there's x squared e to the x. There's no like terms to go with this one. This one can't combine with this one because the powers on x are different. So it looks like we did it, folks. Their survivors are 1 e to the x, x squared e to the x, e to the 2x. So finally, here's our end answer on this. We get 1 plus x squared e to the x plus e to the 2x, all of which is divided by 1 minus x e to the x to the second power. So finally, we got to zoom out on this one to show the whole problem. That's how the derivative of this one will go. Think of this problem as kind of a worst case scenario, but the major takeaways with this one is sometimes there is a lot of product rules, quotient rules, and other rules just mixed together. We have to break it down like this to get to our end result. But other questions? Yeah, go ahead.
So you brought it down, I think you're missing the ECS.
Oh yeah, it was this one right here. So plus at e to the x as well for that last term. Thanks for fighting that one. Probably the better way to convey what's left over would have been arrows. So if you're missing copying things down like I did, arrows can sometimes help out identifying all those survivors. Well, any questions, folks, on getting through that one? Okay, well, we're nearly through the notes. And for the next concept, well, it's not so much a next set of concepts, more, here's what we have so far. It's called a table of differentiation formulas. And the feature about it is, these are just the things that we use all the time. Our goal is to memorize this so that we just take them for granted. We'll always be taking for granted that the derivative of a constant is 0. Power rule always goes this way. And the derivative of e to the x is itself. I think we use this rule probably about 30 times already, probably more. This rule is helpful as well. This is the constant multiple rule, the sum rule and the difference rule. And these two are the two brand new rules. Notice how weird it's written. Sometimes we write differentiation formulas by not saying f of x and g of x. Sometimes we just focus on the functions. It's f prime times g plus f times g prime is our pattern for product rule. And switch to a negative sign, divide by g squared, and you've got your quotient rule. So if you want to state these as fast as possible, that's a pretty good way to do it. And that will be helpful for us to do these next two problems here. These problems are tricky in a certain sense, but they're good ones specifically for really looking at the product rule and the quotient rule and getting a handle on the process. They're not super useful problems in the sense that, well, there's no context at all, and we don't even know how the functions f and g are defined. We just have two function outputs here and here, and two derivative outputs here and here, and that's it. So if we're going to differentiate this thing, it's not a derivative with respect to x either. We're inputting the value of 3 inside there, but we can still use the same sort of process. We have a top function and a bottom function. And so if we look up quotient rule, the one right here, it should go like this. F prime at 3. Then g of 3. So that's the f prime g. Because this is evaluated at 3, we just plug that in right here as well, as opposed to f prime of x, g prime, or g of x. Then if you see a fraction right there, definitely think negative for quotient rule. We'll put in f of 3, and then g prime at 3. Finally, the whole thing is going to be divided by g of 3 to the power 2. So now that we've done that, we have to convey this information into the problem. Let's color code these just so we can see clearly which is which. Now it's pretty much just plug in and calculate kind of a problem. So for f prime at 3, that's the second one for a value of 2. It says g of 3 right here. We have to avoid the derivative. We need to take the function value. We'll put in a value of 5 going on this one. Then rinse and repeat on the next one. It's asking for f of 3. So we avoid this one, that's the derivative. We'll use this one, the function value. So negative 4 goes into that location. Finally, this is g prime at 3. So we're using negative 4 on this. That settles the numerator. So for denominator, we have a quantity to the power of 2. But it's asking for g of 3. And that's because there's no prime right there. So we use the function value of 5 on this one. So again, the only purpose of example 3 is just another way to look at quotient rule and product rule again, and study it from this side, doing a function evaluation all at the same time. Once we get to here, if this was a real exam question, you pretty much have the full credit. It's just arithmetic from here on out. But let's work it out carefully because we know WebAssign is picky with this stuff. This will be 10. There's 3 negative signs, so there'll be 10 minus 16. Denominator is a 25. So this becomes negative 6 25ths. And then the problem is over at that stage. Well, any questions, folks, on getting through this kind of question here? Okay, well, that was so fun. Let's try it again on the product rule version. It's the same kind of idea. We could start off by saying it's equal to. First, we'll differentiate f. That's a derivative at 3. So that's the new weirdness of this problem. It'll be multiplied by g of 3. It's a product rule, so plus in the middle. F of 3, and then g prime at 3. From here on out, the only danger of the problem is now making sure we grab the right values. So we're starting with the derivative, so we'll grab a 2 to start. The g of 3 is going to be this value, 5, ordinary function value. Add to it, oh, and some reason it scrolled on me as I was drawing, that's weird. Add to it, from this position, f of 3 is going to be the value negative 4. Then finally, g prime at 3, we have another negative 4 to throw in right there. So this time, cranking it out, we'll have 10, even in my negative signs, so plus 16. And this one resolves down to a 26 altogether, once we settle on the product rule computation here. We got it, folks. That's, again, another weird way to look at product rule quotient rule. Sometimes people find a lot of value in thinking of it in these kinds of terms. It just forces us to see it as that structure. Any questions at all, folks, on getting through those two? Okay, so we've done lots of product rules, lots of quotient rules. We keep on going through the notes. This is going to be an interesting problem for us to come back to. We'll study this when we return on Monday's class next week. And doing all this work with product rule, quotient rule is not satisfying in my opinion, unless you compare it with a problem where it's of some value. So this is an interesting problem coming from circuits and those kinds of things. If you want to differentiate this, well, that would be pretty important as well. And we need a practical interpretation to go along with it. This one is the hard one. It's a preview to chapter 4, where we'll start using product rules. And when we get the derivative, we'll also set it equal to 0 to try to find optimal values when power is maximized, power is minimized, and those kinds of things. So the major purpose of product rule quotient rule is because we want to do optimization with these kinds of things down the line in chapter 4. But for the moment, I think this is probably a good stopping point for us. We'll return to those additional challenge questions next class time. Any questions or comments at all before we call it a night? Okay, well, it's good to see you all back after the long holiday. After this, we'll be just doing normal classes. I don't think there's going to be any interruptions in the schedule. But have a great weekend again, folks, and I'll see you all next week.